Good day, everyone. So we will start with today's topic, where we will be talking about the taxonomy of RL algorithms, as to how we classify them, why we classify them, and how they are different to each other. Okay, obviously there are different kinds of taxonomies that you will find, but then I will be focusing on the one that is most relevant to our work, right? And we'll be focusing on, as I stated earlier, model-free reinforcement learning algorithms. So the taxonomy starts from that part, okay? The classification of model-based reinforcement learning has been eliminated here for the sake of clarity and focus, okay? Okay. So up until now, we have studied about value-based methods, right? Because what you were doing up until this point was, in some way or the other, compute the value function of the states, right? Or compute the state action value functions, right? Either the V or Q stars or primes, right? You're computing V star and Q star, based on which you are trying to extract the actions that you should take in every state. That would in turn maximize the total expected rewards that you have, which is nothing but the returns. Right? However, this, as you might understand, say for Q learning, okay, what do you do in Q learning? You formulated tables, right? You have the state and action, and then you had A1, A2, whatever, S1, S2, whatever, right? And for every pair of this state and action, you had some number. Right? And for every state, you basically simply had to choose the maximum numbered column here, which would correspond to that particular action. Right? And simply you string together all the actions and you formulate your policy. And if this corresponds to the maximum numbers here, it would be the optimal policy. Clear? That is what you were doing in value-based functions, okay? In policy gradient methods, however, the next classification that is you will not worry about the value functions. You will not bother computing these value functions. Rather, what you will do is, you will directly change or tune rather the probabilities of taking certain actions in certain states. You get it? Okay, now what do we mean by this? Again, we have another table, let's assume this way. State and action, okay. A1, A2, whatever, S1, S2, and so on, okay. Now here you write some probability, and so on. Here this number does not correspond to your action value function, the Q values. Okay. Rather, these numbers are the probability of taking that action in that state. Clear? Okay? This does not depend on the system dynamics. Okay? Because in any given state, you can take any given action. Right? Now, with what probability you will choose that action is up to you. Right? And when you are the optimal policy, you will be tuned in such a way that you will maximize the probability of taking a certain action in a given state, which would in turn give you the maximum expected return. Right? So here you are not computing the value functions explicitly. Right? Rather, what you are doing is you will simply make sure that you take enough actions, okay, or take some actions with some probabilities, and at the end see the expected return, okay, and then see whether how good or bad that is. You again repeat that for a different set of actions, again different set of actions, again different set of actions, by simply changing the probability of taking the actions here, right? When you run this enough number of times, that is infinite times, then you will converge to an optimal policy, which would then tune this values of probabilities of actions such that you will, with a very high probability, take a optimal action in a given state. Right? Okay. Clear up until this point? Okay. Details I'll go further. I'll go later. Now coming to the actor critique method. Okay. In actor critique method, okay. Value function was what? Simply computation of value functions, and based on that you could do it. Action function, you simply tune the probabilities here, right? Here you don't care about the value functions. Here you don't care about the probability of taking actions, because you assume you will deterministically take the best action in every state. Now, actor critique method is a hybrid of these two methods, value function and policy gradient methods, right? What it will do is, as the name suggests, there are two components in it. There is something called an actor and there is something called a critique. Okay. Now, what do critiques do generally? You might have heard food critique, movie critique, or there are a number of critiques. What do they do simply?
Criticize the action.
Yes. So they simply say whether how good or bad that thing is, right? Exactly. Even here, the critique will simply tell how good or bad that action is. Okay. But remember earlier, okay, what is your metric for telling whether the action is good or bad?
The return.
Return, right? So critique now somehow depends on a return, right? What was value function dependent on? What are value functions rather?
Return.
Yes, they are the expectation of the returns.
Yes.
Right? They are the expectations of the return. So critique is the value-based part of your actor critique method, right? And actor itself, actor from the name it suggests that it is taking some action, right? It's not the actor, it is something that takes the action, okay? So this thing is directly focusing on the policy, right? It will, in this way, take some actions, okay, based on whatever probability it is to take that action in that state, okay? And it will wait for the critique's feedback to tell whether that is good or bad. This plus this will give you actor critique, right? That's the entire concept in a nutshell of value-based, policy gradient, actor critique methods. Are we clear on this up until this point? Okay? So this is how you could classify it. Okay, model-free methods classified into three categories, and within value-based method you again have different methods of computing the value function. Okay, and here SARSA and Q learning uses TD learning, okay, to compute the value function based on TD learning. We'll be studying about reinforcement. Now reinforce, though it is under policy gradient, it is in some way related to Monte Carlo. Okay, how, why, what, we'll do it later on in the coming slides, hopefully today's lecture. Now there are multiple policy gradient algorithms, a few of them are listed here. Similarly, when you come to actor critique, again there are different algorithms, right, that uses the actor critique methodology to obtain the optimal policy. What is the ultimate goal of reinforcement learning? To obtain the value functions or the policy? Policy, right? So that is why in policy gradient you don't even compute the value functions, because your end goal or your main objective is to simply get the optimal policy, right? Whether that includes the computation of value function or not, it's irrelevant to the goal of reinforcement learning. Clear? Okay. Yes.
You said that the actor critic is a combination of both value-based and policy-based. Explain that again, please.
Okay. Actor critique methods, you have two components. One part, the active, the other part, the critique. You will see when I talk about policy gradient, there is some, there you are relying on the returns, okay, not on the value function. When you're relying on the returns, it means you're waiting for the entire episode to roll out, which is nothing but Monte Carlo, right? Because Monte Carlo wants you to complete the estimate fully, okay, and then take that value rather than an expectation. Okay? Okay. In actor critique, what you do is you can use these values as well, the estimates. There is another estimate that is involved, which I'll talk about when I get to the actor critique method. But basically, when you have the estimated version of policy gradient, that forms the actor component of actor critique method.
Which part forms the actor?
The estimated part of policy. Okay. What's the difference between Monte Carlo and TD learning?
Monte Carlo
And TD learning?
and TD.
Yes.
Monte Carlo you do a full episode, right?
Yes. And in TD learning?
And TD it's an estimate.
It's an estimate. Okay. So the actor part of actor critique and policy gradient methods are basically Monte Carlo and TD learning, exactly like that. Okay. The actor part of policy of actor critique method relies on an estimate for changing these probabilities of the actions. Okay. Whereas the critique part, just like normal value-based method, it will estimate the critique, the value function that is. Okay. And these two work together to improve the optimal policy, improve the final policy that we are getting.
So the actor will do the estimates, will rely on the estimates.
Will rely on the estimates to change the probabilities here of these actions.
Okay.
In given states. And critique will simply tell how good that, so actor will take series of actions, formulate a policy, give it to the critique will be like, okay fine, not good, good, very good. And based on that, the actor will keep changing this probabilities here.
Yeah, that is obvious from the that whole model which is repeated under a different name in machine learning, like you mentioned before, I think.
Mm-hmm.
But the point here is you've said that it is like actor critic is a combination of both, right?
Yes.
So value based and policy based, right? So and then when you explained it right now, you said that okay, that boils down to the estimates as opposed to the
the actor part of actor critique method, not the entire actor critique method.
Mm-hmm.
Just the actor part, because the critique part is still value based. The actor part of actor critique method is analogous to the policy gradient, but in an estimated version, just like Monte Carlo and TD.
So like policy, like here, policy based?
Yes. Here, when we are talking about policy gradient methods, how do we change the probabilities or tune the probabilities here? That is relying on the returns, which is the actual returns, right? Not estimates. However, the actor part of the actor critique will not rely on this returns, rather it can use expectations. Okay? And the critique, just like normal value-based method, it will use the estimates to compute the value functions, and then it will tell you this is what your value function is. It's good, it's not good, it's very good, it's bad, very bad, whatever it is. The actor will then keep tuning these probabilities, tune the probabilities to maximize the probability of an action which is good in that state. Right?
And the critic, and you said it relies on the returns, right?
Returns.
And so in that sense, that is considered what?
The value-based part.
Okay.
Critique is the value-based part.
And then the actor will be the policy based.
Yes, exactly. Yes.
Yeah. So, like, what is the main purpose of policy gradient methods? Like, why do we come to policy gradient instead of the value based?
Okay. Yes. Give me 2 slides. I'll get to that point. Okay. But that's the first point that you will be studying as to why policy gradient. Okay. Yes. That's a very good question and a very valid question. Just to summarize, so your value-based methods, you compute the value functions, right? And from this, what do you understand? For what kind of things you can make these tables? For discrete, like if discrete spaces, right? Say if you have infinite actions, can you make such tables?
No.
You cannot, right? However, now comes the part where, okay, let's skip this because, okay. Policy-based methods targets the weaknesses of value-based method. Okay, in the sense that here you need this argmax argument, right? What does that do? That tells you which action, the index of which action is the best one. So you need basically a finite space for that. Whereas with this thing, policy gradient methods, You don't have to worry about that. Okay. A table here is just an example basically, but then it's just probabilities. You can have any number of actions, and what is the rule of probability? The sum of probability should equal to 1. You can have any number of elements in that sum, right? So policy gradient methods do exactly that. They will enable you to use continuous spaces, right? Which you couldn't do with value-based methods. Clear? Okay. Yes. Also remember, we used epsilon greedy exploration method when we were talking about Monte Carlo and TD learning, right? So we had to inject exploration into that, right? Otherwise, inherently it is deterministic. It will always take the given action, right? We had to inject disturbance to that, or yes, disturbance to encourage exploration. However, you see here this works on probabilities already, inherently. So policy gradient methods are stochastic, therefore better exploration. You don't have to explicitly worry about injecting some exploration strategy into it. Clear?
So the policies are predetermined.
Sorry?
The policies are not predetermined.
Okay, so by policy, what is policy? Actions, right? A1, A2, A3, right? But here, it is okay. You mean predetermined what? Like this set of actions is fixed or not fixed?
Yeah, because in value-based approach, we already have the policy part.
Yes. There, no, you will not. There, it will depend on this probability. Like every time the policy is formulated, it depends on the probability distribution. Get it? If the probability is higher, that action might be taken more number of times. If the probability is lower, it might not be taken that many times. Right? But at the end, the learning will be complete when you have visited all the states and completed all the actions enough number of times, right? To avoid local minimum.
When you say TD, you imply Q learning, both Q learning and SARSA, right?
Yes, Q learning and SARSA are basically the same thing except for they are on policy and off policy. Right? Yes, this is different policy. Okay. So what exactly do we mean by changing these probabilities? Basically what we are doing is we assume these to be some parameters, okay, and we are trying to tune that parameters to so that the output that you get is the optimal, right? When it is a neural network, okay, when you will be studying about deep reinforcement learning, these parameters are simply the weights and biases of the neural network. You have to make sure that you tune the weights of the neural networks such that it becomes the optimal configuration, right? So that you get the optimal policy as the outcome. Clear?
Doctor, in the slide before, I was thinking how we evaluate it's an optimal policy. I think it's via the return to, I mean this equation we passed over.
The delta J equation?
Yes. Then I know the word, but this is the gradient of what?
I will come to it. I just put it here, but then there's a derivation for it. We'll do it. Yes, this is the actor critic method. Okay. This is just basically when do you choose what, right? If you have a discrete setting with low dimensionality, you can choose Q learning, which is very good because you simply get a table. Basically, it becomes a lookup table, and you pick the actions that gives you the maximum numbers. However, as the dimensionality and complexity of the problems increase, you need to now rely on something more advanced, and there steps in policy gradient, okay, or even actor critique for that matter. Okay. Now I will go to the next. And by the way, we do have numerical on this policy gradient, so I'm giving you a disclaimer beforehand. You will understand the concepts better, hopefully when that starts. Okay. So why policy gradient like you asked? Yes, because it is better at handling continuous spaces, okay, be it action or state spaces. And then you have stochasticity feature, like I said, inherently stochastic because there is a probability distribution here, unlike the deterministic version in value-based methods, which will give you exact action for exact state, right? Or one action for one state, basically. Now, to understand policy gradient, you need to very clearly understand what policies are. Okay. Again, what are policies? Okay. The reason why I want to stress on this again is because in midterm, there was a question related to this. Okay. I gave you a policy, if you remember. It was something like this. Right?
Yes.
What does this mean?
Set of actions to start.
Set of actions.
Left, right, left.
Yes, that is, you're in S1, you take N. And the problem was deterministic, implying if you take a certain action, you will, with certainty,
Reach.
go to whatever the next state is corresponding to that action. Right? So here, left, right means you will start in S1, you will take a left, go to right, then again left, then right, then right. Right? So what is a policy?
Set of actions.
Set of actions, series together in the optimal way. So here, every action will have certain probability. Okay. In a deterministic setting, what will be that probability? 1. Right? For every state, you will have 1 for every action. Right? However, now assume that these actions are not deterministic.
For every state, you will have 1 for one action, and the rest is going to be 0, right?
Yes, if it is a deterministic situation.
Right.
However, with policy gradient methods, you do this basically. That is, you say not every state has one action deterministically, right? You can take any number of actions, okay, with different probabilities, right? That doesn't mean the action will change the state that you go to. That's not the transition probability. Okay, there's a difference between the transition probability and the action probability. What is the transition probability?
The model of the environment. Itself.
Model of the environment, right? Can you change that?
No.
No, you cannot change that.
The dynamics.
Yes, that is the dynamics of the system. However, you can change the occurrence or the probability of an occurrence of action happening in a given state. That is something that you explicitly do. You get it? That is, if you are in a given state, you can take different actions there. That is under your control, right? And that is what the policy will target. The policy will exactly try to do that. Change the probability of taking a certain action in a given state. Clear?
So that is as opposed to transition probabilities. So the probabilities of the actions here, what do you call it?
This is simply the probability of actions. There, that is something inherent of the system dynamics itself, right? We cannot change that. That is beyond the control of anyone, right? You cannot change how the system will react to given an action. But you can control which action to take so that the reaction that you get is what you want, right? This is the difference. Clear on this? Yes.
Is this applicable to continuous actions?
Absolutely.
I'm trying to think. If it's a discrete action, I understand. What, like, a robot in S1 can go, for example, with probability of 0.1, go up, then go down by another probability, and so on. But if it's continuous action, how it will be calculated?
The motion that you're talking about is the transition probability.
No, I mean with, for example, I'm standing here.
S1, okay.
I'll move 0.1% of the time, I'll move up.
Yes.
0.7% of the time, I'll move down.
Okay.
This is action probability.
No, that's the transition probability.
No,
Because
I mean,
that
I'll
has
take
to-
the action with 0.7 probability.
Okay, okay.
I know, I'm not talking about the states.
Oh, so you mean you're in S1 with 10% chance, you take an up action with
Yes.
70% chance?
This is the table. What
Yes,
is
this
the
is
table
that.
like?
Yes,
Exactly.
this is that.
But what if the actions are continuous?
It simply becomes a probability distribution.
Okay.
Right? Not numbers, it's a probability
Yes, if I was
distribution.
thinking of it like this, it will not work. Only a
Yeah, yeah.
probability
Then
distribution.
obviously even this is applicable only to discrete systems.
Okay. Yeah.
Okay? So yes, so what you want to do now is, you want to, these are your parameters, you want to change the parameters in a way such that it, what does it do?
You get the optimal policy.
And by optimal policy you mean what? How do you know it's an optimal policy?
Highest return.
Highest returns, right? Highest returns, not the expected returns. When there are expectations, then comes in the value functions. If it is the returns, it's simply the returns, right? It doesn't have to do anything with value functions.
What is theta? Or I know what is theta, but I mean it's saying to optimize theta to get this.
Again?
To optimize theta, when we use deep learning, you mentioned that we parameterize
Yes.
with such.
Yes. In this case, what are thetas?
Yes, exactly.
These are thetas.
Okay.
These
So-
numbers are thetas basically. You get it?
So each action step here is or action in this.
Each probability of an action is a theta basically.
Okay.
Okay? Okay. Now according okay. Now comes an interesting concept of credit assignment. Okay. Now, sorry.
No, sorry. What's credit assignment? I was thinking of it.
Yeah, I'm coming. Okay. So what do you mean by credit assignment? Here, what are you doing? The thing in policy gradient is you are waiting for the entire episode to get the feedback on that action. You take one action, you get the immediate reward, that's it, but you're still not, at that instant, you don't know for tuning the, tuning the actions, right? You tune the probabilities, you tune the stable only when you get the entire returns. So there might be one action which would lead to say 5 different consequences because of the later actions that you take in that series. Clear? Okay. Now assume from here to going to that goal, there are 10 steps I can take. Okay. Me moving forward straight at 0-degree angle is a very good action, right? At this point. Why? Because I am going towards the goal. However, if I do not again go forward and move somewhere else, which is away from the goal, does it mean that this action is bad? The one that I just took, where I move forward? No, it is not. Right? The next action is bad. Right? But then when you are waiting for the entire return, you simply get for the entire path, this is the value. Right? It would then mean that the entire series of actions are bad. Okay? So if you rely on that simple number, what would happen is, you'll be like, okay, all the actions in this series are bad. So I will not take that actions. So you will not move forward towards the goal. Now you will move somewhere away. But next episode, say, you see that your one action is bad, okay, but your remaining episode is good. Then you're actually moving towards the goal, reducing the distance, right? So in that case, what happens? Your return now is better. You would simply assume that that is your optimal policy. But is it your optimal policy? No, right? So, and individual actions will not have any consequences basically, right? You somehow reach the position where you get a good return, even if there are suboptimal actions in between, it would simply mean that you are getting the optimal policy.
Can you say that again? Individual actions what?
Individual actions will not have, you will not understand the impact of individual actions if you're simply waiting for the entire return, right? And then you are like, okay, fine, this series of actions are good. So in between, in the policy, like here you have a policy, right? Say one of these actions is suboptimal, right? But the return compared to the other policies is better for this policy. That would then mean that you would choose this to be the optimal policy, when it is not, because there is one suboptimal action in that, right? So in order to negate this problem or overcome this issue, what is done is something called credit assignment. Okay, that is, the reward is propagated backwards for every action. Okay, clear? Here you are like, okay, fine. When I move forward here, when I get the entire return, it is formulated in such a way that when I see the feedback, I'll be like, that action at that time was good because your reward increased at that point. But your subsequent actions were bad, which led to a lower return. Clear? Clear? 100%? Yes. Okay. What we mean here is, say I move forward one step, okay, and I want to go towards that door, okay. Me taking this action, is it a good action or a bad action? It's a good action, right? Because I reduce the distance now. But after taking this action, for some reason I start wandering somewhere and I take a big path to reach there. Right? So now I have taken more actions, which is a bad path, which is a bad policy, right? I should simply walk straight, okay? So, but because of the way policy gradient works, you are waiting for the entire returns. It is Monte Carlo, right? So you have to wait for the entire episode, and then you tune your policies, right? So if you get simply a number, you'll be like, okay, that policy is bad, implying all the actions in that policy are bad. So you will not even take the step forward. Next action or next episode, what happens is, you take one step to the left, and then you somehow take a policy which will directly take you to the goal. You get a higher return, right? Then you will be like, okay, fine. So this would mean that my policy is better now because I got a higher return, right? Also, you could then argue, I'll just come back to that point. You could still then argue that ideally you should have computed the state action infinite times. That way, this should be balanced, right? It should take every action in every state into every possible combination. But is that efficient?
No.
That does not, right? So that is the reason why you have credit assignment, right? Then you start weighting individual actions in every state, right? So then what happens is, you start trying to backpropagate the reward that you get, the return that you get, to every individual action. You're like, okay, fine, up until this point, the reward was good. So something happened from this point onwards that reduced the reward. So then you'll be like, okay, no, probably till in this state, this action increased the probability. It is a good action. But from there on, the actions that you took are bad. Or maybe 2-3 actions were good in between. So this actions are bad, this actions are bad. Reduce the probability of this action, reduce the probability of these actions. Increase the probability of this actions. Right?
So the credit assignment here is like obviously we're talking policy based. Right?
Yes.
So we have the full episode.
Yes.
And then thus, like I would assess every action along the way.
Yes. Yes. So there's an equation which I'll show in a couple of minutes. Then you will understand how this happens. And there's a derivation as well. Yes.
So instead of the return being a scalar quantity, it's a like sublist type that like encompasses the goodness of each action.
How do you know it is good? What is goodness?
Like based on the return. So
which is a scalar quantity.
Yeah, like a scalar quantity in the sense like for the full episode usually.
Okay.
Yeah, but here you are saying that for each action we are measuring how good it is.
We are not measuring. We are not measuring. We are simply inferring for each action for each state how good that action was, based on some equations which would backpropagate the reward that you got.
So that result is differently like backpropagated instead of the return, like alongside the return.
Based on the return, it is backpropagated.
So there are some quantities that are stored for each action in that policy.
Yes. Yes, that is what you are doing. You basically are trying to improve the probability of an action in a given state. Right? Clear up until this point? Yes.
Yeah. So what I mean to say is that it's not a single scalar quantity, but is it a like multiple scalar quantities?
I don't fully get it. Okay?
Like if it's the full episode and you get one return, so
Okay.
that is a single scalar quantity.
Oh, you mean it's a vector, not a...
Yeah, vector instead.
No, it is a single number. Because you multiply it with certain terms, which would give you for every action what's the corresponding value. Right? So no, it's not a vector. It's a single value vector. Yes. Okay. Okay. So here, again, you follow gradient descent method to tune or to change the parameters theta such that you get the optimal policy. Right? And again, you will see that you have a learning rate You have the returns, and then you have a gradient of a certain term, right? That term will come to it. Okay.
Why do you say gradient ascent, not descent?
Similar like propagation.
It's because based on back propagation. Yes. It is. Oh, so you okay? Okay. No. That the parameters theta. You don't have to only increase it. You simply have to reduce the loss based on whatever.
Theta here is the probabilities.
Yes.
Right.
Yes. So it's not necessary that for every state action pair or the action that you're taking, you have to increase the probability. Maybe you have to decrease the probability for that as well. Okay.
Right.
I'll come to it. Okay. Your objective, like in any RL problem, is to maximize the total expected return, right? And okay, you're applying gradient descent, right? That's a plus. So you apply gradient descent method based on the return that you get, okay, to tune the parameters such that you increase the probability of taking a certain action in a given state. Is this part very clear? Because the entire concepts that we'll be studying from here on will depend on this idea, right? Clear? Okay. Now these probabilities, okay, I can simply put some numbers here, which might not sum up to 1, right? Because say if there are many actions, I cannot give individual values to all that, right? However, I can simply give numbers randomly, 10, 15, 20, 5, 1, 2, 3, 4, whatever positive numbers, okay? And that number would simply mean, a higher number would mean the probability is higher, okay? So in order to, okay, what's the law of probability? It states that the sum of probability should always equal to 1. So for that, we use something called softmax, right? You plug in your thetas for every action into this equation, and then you will get the corresponding probabilities for that. Okay? You don't have to worry about optimizing the probabilities directly. You could simply optimize the numbers, increase or decrease that number theta, and the softmax part will take care of the probabilities. Right? Basically, that's something that's happening under the hood. Everything happens under the hood anyways. But here you don't have to worry about changing the probabilities. Right? You simply have to change the number theta. Right? The probabilities will be taken care of. Yeah, why softmax? We just discussed about it. Plus, it is a differentiable function because there's a gradient involved, right? There's a differentiation term, a derivative term involved. So for that, you need differentiability, right? Okay. Again, your theta does not depend on the environment dynamics. You are not changing the transition model of the system. You are simply tuning the probability of taking an action in a given state, right? Which would then be formulated as a policy. Clear? 100%? Okay.
So I'm still not clear on the ascent part, like that's we're adding the term with the nabla.
Okay.
Like shouldn't we be going heading downwards?
Why should we be heading downwards?
Well, I'm maximizing, right?
Okay. It could be the same thing as well. If it is like this, the hill, you simply want to go uphill to the max point.
Yeah, but so it's a max. Is it because it's a max?
Because you're trying to gradient descent will give you the max.
Maximize the gradient.
Yes.
The return.
Max. Yes. If it was a cost function or a loss function as in controls, then you would have this problem.
Yeah, probably. Like what you do is you end up doing the minus, like because it's.
In fact, that is what is being done. Yes. Yeah. Yes. Because descent is a lot easier than ascent.
Yeah.
So that's why. But yes, here
But the standard in optimization is
it is the same. Yes, obviously. Okay. 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 Now here comes how we compute the gradient. Okay. So this is your return. This is your probability of taking an action. Okay. Down here is the trajectory. What is a trajectory?
The final outcome.
policy.
This is your trajectory. You form a.
Tuple.
Sorry.
A tuple, for example.
No, you have a. Yes, it does a tuple as well. Yes, but here you form for 1, say 2, 3, 4. You stack many of these together. Every instant of this is called a trajectory, right?
Why? Why are you calling that? And is it SAR, SAP? Or do you have an A by then?
So without the
Why?
because then it depends on. You could have any as well. In fact, you do have any, but this A depends on whether it's on policy or off policy. If it is the action from that policy or not, right?
Okay.
So why you don't have explicitly have to write action here, because for you don't have to worry about what next action you're taking every time. You simply need to know what next state you're going to, right?
Under policy based? Or just
Even in action based, sorry, even in value based, you don't have to worry. Oh yes, there you have to. Yes, there you have to, because you want to compute Q, right? Which would include the next action and state that you will take. Here you don't have to worry about that. Here you will simply assume, because it depends on the returns, you will anyhow have a deterministic action that you are taking. At the end, you will get this. You're like, okay, in this action I took this, in this state I took this action, I got this reward, I moved to this state. And you compile a list of these trajectories.
And why do you call that tuple the trajectory?
It's named that way. It's named that way. Right here. Okay. So when you are trying to compute the derivative of this, okay, you take differentiation on both sides, you apply something called a log trick here. Now why do you apply this log trick here? Because we want to do, here you're taking log here, okay? Log of this probability. So when you're taking a log of a positive number, you will get something this way, okay? But why are you even converting this part to this? Why? For some sort of calculations ease, right? Whatever we do is usually to ease the compute. Why are we, okay, when you have some kind of product of sum, POS, right? You tend to take log for it. Why?
Because to reduce sum of them.
Yes, then it would simply convert it to sum of products, right? Why? Because it is easy to calculate sum rather than products, right? So even here, because now, okay, what are you doing? Remember, this is for every trajectory. Every trajectory is one rollout of the entire episode that you have, right? So you basically want it for every trajectory separately, not worrying about the entire episode, right? For that, it is easier to compute for log rather than the entire trajectory, okay? Rather than the actual term, that is P of tau, okay? Yes, exactly here, because your probability is a product of sum, right? When you take the log, you basically simply get a sum of products. Now it is summation, which is easier to handle, and based on that you will compute now this gradient. Okay? Now this gradient, you see here, this is your probability, action probability. Taking what action in what state. This is multiplied by your return. Okay? This would help you in doing the credit assignment. Backpropagating your return, total return that you get, and pinning it to every action that you took in that state. Clear? Clear?
So,
Yes.
does the return only depend on the current reward or the cumulative reward? It was g of
Tau.
tau. Yes.
It is for that instant basically. But here you want it for the entire episode, right? That's why you sum it. You take GT, okay? You're taking GT, not G0, because you want to make it independent of the past, right? So for every action, you're like, from this action onwards, I got this return. From this action onwards, I got this return. That way, you will be able to exactly pinpoint at what point or from what point onwards your return did not go very good, right? So this is how you do exactly the credit assignment part, okay? It's not G0, it is GT, because you want to see how your return changes after every action, right? This action, return was this. After this action, my return was this. After this action, my return was that, right? Because say probably you're taking good series of actions, okay? Your return will increase. But after that, your return might keep decreasing. So you know that till this point in the trajectory, the actions were good. So increase the probability of those actions in that state. But thereafter, go on reducing the bad action probability. Clear? So this is a very subtle yet a very important thing here that we do. Okay?
Doctor, where we are actually using this credit assignment, like in which algorithm, like in actor critic method?
No, in policy grading method.
In policy grading method.
Yes.
Okay.
Yes.
So in like it will be used also in actor critic methods on actor part.
Absolutely.
Policy grading method.
Absolutely. Yes. Yes.
And doctor, I have another question, like the softmax
Yes.
policy, what you mentioned, like where it is used in this equations, or it will only use for calculating the probability?
No. Here you have the thetas, okay, which could be any numbers. You don't have to worry about summation of that numbers to 1. Okay, in order to take care of that, so that it complies with the probability rule, law of probability, which says that the sum of probability should be 1, you use softmax. Okay? Clear? Now comes an algorithm called reinforced. Okay? Reinforced is a Monte Carlo based policy gradient method. Okay? Why is it Monte Carlo?
It's the full.
Yes, it uses the full episode returns. Okay? And then based on the equation that we just saw, it will assign the credits to every action. Okay? Clear? In this, what we are trying to do is, again, obviously, maximize the expected return to obtain the to get the optimal policy by tuning these thetas. Right? Clear? Okay. Let's just that. Yes, the reinforced update rule is exactly same as for any standard policy grading methods. So simply a comparison here between Q-learning and policy gradient and value-based methods, okay, which we already did talk about. Now I will do an example for reinforce.
So why do you call it reinforce?
It's just an
So reinforce basically is Monte Carlo.
yes.
And policy based. Policy based.
Policy based, yes, okay. Again, a very simple problem where you have two states, okay, S1, S2. In S1, you take A1, you get a reward of 0, you go to S2. In S1, you take A2, you get a reward of 1, and that's a terminal state then. You go to A2, in S1, you take A1, you get at plus 3, you go to a terminal state, say S3. In S2, you take A2, you get a reward of 0, but it ends up in the terminal state. Okay? Clear? So, what you do is, your discount factor is 1, okay, learning rate 0.5, and you can take, initially, you assume that the probabilities of actions in every state is 50-50%. That is, you can take any of the actions with equal probabilities. You can either take A1 or A2 in S1 and S2. Okay? Okay. From the first episode, what you do is, say you choose A1. Okay? For A1, A1 the reward in S1 was 0. Okay? So your reward is 0, you move to S2. Again in S2, say you choose A1. The reward for choosing A1 in S2 was plus 3. And you go to terminal state. Okay, that's what it says. So your total episodic reward is how much in this case?
Plus 3.
Plus 3. Okay? And you do exactly that. Now you compute the gradient. Okay? Take sorry, there is no minus here. There is no minus here. It is simply minus 5 theta. Okay? When you take derivative of this log function, the policy function, with respect to action A and A star or A dash, that is A1 and A2 in this case, you will get 1 minus pi theta and minus pi theta. This is for A1, this is for A2. Okay? Clear? When you take it, what was the probability of taking A1 in S1? 50%, right? So 1 minus 0.5. For the second one, it is, again, what's the probability of taking A2 in S1?
It's 2.
No, A2 in S1. You see, it is A star, A dash, but in S.
Okay.
Again, it's 50%, right? But here you have minus sign preceding it, so it is minus 0.5, okay? So now your derivatives are plus 0.5 and minus 0.5, that is the gradients, okay? Now applying the reinforce update rule here, your learning rate was 0.5, yeah, 0.5, right? Yeah, 0.5. Your, again, your initial estimate, learning rate is 0.1, is it? Yeah, learning rate is 0.1, alpha is 0.1, okay? Your gradient as you computed this term was 0.5, your return was 3 for A1 in S1. Similarly, for A2 in S1, your theta, this term, the second term would be what? 0.1 obviously the learning rate, but now the gradient is minus 0.5 and return is obviously same 3. So you get some other number. Okay, you do the same thing for S2. Okay, S2A1, S2A2. Okay, you get some values here, some deltas. What was your probabilities? Your theta was 0.5 and 0.5 for A1 and A2 in S1 and S2. Okay, but now based on this update rule and these computed values, you will update your parameter space such that your S1 in A1 now is 0.65. S1 theta 1, S1 A1, S1 A2, S2 A1 A2. Now the probability will increase to 0.65. Okay? Whereas, yes. Yes, but in this case, it is, yes, okay, it is theta. So theta will become plus 0.65, whereas for this one, it will become 0.35. Okay?
But we say theta initialize at 0, so it's the difference. We have to initialize theta first.
Which one?
C.
C?
Theta.
No.
Initialize theta with 0.
Theta you can initialize.
How we update theta if we don't have an initial value?
That's why you initialized it to be 0.5 and 0.5 here. You remember?
No, actually, we go with a 0 here because
This is the delta, not the theta.
the C.
Hey, it's written the delta.
No, it's down.
Oh, this one here, initial parameters.
Yes.
Okay, you could initialize it to 0 or 0.5 as well. It doesn't matter because the update will be in such a way that the good action will increase. The probability of good action will increase. But yes, okay, it's 0. You would simply get okay, then it will be okay. 0.15 minus 0.15, 0.15 minus 0.15. Okay. Now based on these, if you compute the probabilities, so probability of action A1 okay, would be 57.4%. And probability of A2 would be the complementary value, right? 1 minus of that thing, which is 42.6%. So in both cases, your probability for A1 will increase. Why? Because if you take A1 in either of the states, the return that you're getting is more. Clear? Yes.
Does the equation we use calculate the theta, the total probability, or the delta? Because there it's written delta, so I was a bit confused. It's the delta either increase or decrease on the initial guess.
Yes, but here your initial is 0, so whatever delta you have is actually the value.
I mean, if our initial is 0.5.
Yeah, this part is delta.
Okay.
This part, here what you're calculating is delta.
Okay, so this equation is for the delta.
Yes, for the second part of,
Okay.
this RHS equation. The second part of the RHS of this equation. Clear?
Another point, from what I followed, we took A1 in state from state 1 to 2, like the 2 times we tried A1, right?
Yes.
But we evaluated A1 and A2, but I don't remember that we tried A2, so we saw what is the total reward.
Okay, go on.
We tried A2.
We did not, because we need.
Yes. We didn't try A2,
In the
right?
next episode, we'll do that.
So how we got it to minus 0.15 if we didn't try it? This is I mean, how we evaluated A2 in otherwise.
Okay. Here, probably, if the action was better in A2, okay, in the next episode, when you take A2 only, okay, your probabilities would increase for A2 and decrease for A1. It is just a coincidence here that you're taking A1. So now you're asking, why are we even evaluating A2 if we haven't tested A2?
Because next action, if we would call it next in this one, here we have 2 actions. But
Yes.
generally we have more, so
Yes.
we work sequential. Like, I mean, what is the next action?
Okay.
We
So now, from what I understand, you mean we did not even take A2. So why are we changing this for A2?
in value function calculation, we work backwards. So I understand the iteration or the recursive part.
Yes.
But here I didn't get that how we work back, how we know the next action even.
We don't know the next action. We don't care about the next action.
So I mean, how we did it as when was A prime and S prime. We know the next state maybe, but I mean, there was a part of A prime and S prime.
A prime is not the next action. A prime is basically the other action apart from the main action A.
Oh, okay.
Okay, it's not the next action.
This is what I'm asking about.
No, it's not the next action. It is just the other actions that you have. Okay.
Okay, I got it.
So, but still, okay, just to add to it, now why we did not even take A2, right? But we still reduce the probability of A2 without even taking that action. Why?
A1 increase, we got to
Product probability have to be
So
Because with A1, you see the return increased. So you are like, okay, fine. A1 it increased, so I'll take A1. Probably in the next episode, I'll take A2 and then I'll see the return. And if again it increases, I'll simply increase the probability of A2, then decrease A1. Clear?
And if it's another, if we have 10 actions or so, we include all of them or decrease all of them?
Yes, we decrease all.
That's good, yeah.
Yes. So because of softmax here, now you see, you simply have theta here, which doesn't sum up to 1, right? It is 0.15 minus 0.15. In fact, it sums up to 0. But still, because of your softmax, you get probability distribution, right? You're like, okay, fine. Now, if you are in S1 or S2 in this case, you take A1 with 57.4% probability, right? So that's exactly how you will do multiple iterations again, obviously, till you get a constant value. Till the values have converged. How do you know the values have converged?
They don't change.
They don't change. Clear? Okay? Okay. So
Are you going to publish this?
yes. So